Bismillahirrahmanirrahim. Hello everyone. This is the part 2 of the Fourier analysis techniques chapter. In previous part, we studied the Fourier series analysis. We tried to determine the basic equations of the Fourier series analysis, and after that we managed to find the series of some signals that were composite signal. Composite signal means that they were the combination of different frequency components, and later on we discretized those components and found the magnitude and phase of each component. So that was Fourier series analysis. In today's lecture, we will discuss the application of that specific Fourier series analysis in our electrical circuits. Since our electrical circuits are mostly energized by periodic voltages and periodic currents, so that's why we will determine the dissipation of power in those circuits. Also, we will discuss the Fourier transform and Fourier transform pairs for different electrical circuits, and we will discuss that why it is important and how it differs from the Laplace transform. So these are pretty much our today's goals. Coming to the contents of this lecture, we will first apply our previous knowledge on the Fourier series to the electric circuits, and after that we will find the DC and AC dissipations. It will be in terms of either voltages or currents or power. So it will majorly involve I of t, V of t, and P of t. So we will find these things. Beside this, we will calculate the basic mathematical formulation for the Fourier transform. We will discuss the concept of Fourier transform and discuss the pairs, the transformation pairs for Fourier transform. We in general discussion we write it ft to reduce our effort in writing it. So Fourier transform is ft, and in case of inverse Fourier transform it will be IFT. Inverse Fourier transform and Fourier transform are just similar. After that we will solve some examples on the Fourier transform. Let me share this with you that Fourier transform is not a part of the circuit analysis 2 curriculum, so that's why we will just go through it, skim through it, and after that we will solve at least one problem for its application in circuits and systems. So in the last we will do this thing. So coming to this application of Fourier series concept to general circuit, let's say we are having a circuit, we are having a network like this. In this network we are having different sources here, V0, V1, V2. Now you may remember that in Fourier series we didn't have separate sources. Instead we have a singular voltage V of t or X of t, and that X of t was, let's say, determined by a periodic function. Let's write it as 1 from 0 to less than time period less than t0 by 2, okay, and 0 from t0 by 2 to t0. So I'm confusing it with this thing. Let's say this is t by 2, and this is t by 2 to t. Now this is a bit better. So let's say we are having some signal like this. We can write it as this. Okay, so time starts from 0 to t by 2 and goes from t by 2 to t. So this signal might look like this. 0 to t by 2, it is this and this. So this is our signal, let's say, and it will repeat itself like this and like this. So for now we are having this structure of v of t. If we apply Fourier series on this thing and find its Fourier series, if we apply Fourier series form transformation on this and find its Fourier series, we will get v0, v1, v2, v3. Now these things are not separate sources, but these things represent separate sources of a frequency 0, a frequency f, 2f, 3f, let's say. So this thing is elaborated in here, that we are having separate sources v0, v1 up to vj of t. So these are not actually separate sources, these are just a single source v of t, but due to the ease in Fourier transform, Fourier series, we converted this f of t to different functions, let's say v1, v2, v3 and so on. So this is pretty much it. Okay, so we had this signal, and what we actually did is that we transformed it into different components. Okay, let me clear up this mess a bit. Okay, so majorly if we have such scenario, so we can write the voltages as the DC voltage with 0 frequency and all the components which are represented by the n term. So put n is equal to 1, 2, 3, 4, 5 to get the values of this thing up to infinity. Okay, similarly the current can be the DC current or the frequency based current, the AC current, which can be calculated from the n value. So n naught, n omega naught means 1 on omega naught, 2 omega naught. It can have all the terms 1, 2, 3, 4, 5. It can have odd terms or it can have even terms. So it depends upon the signal and its structure, which are dealt in odd, even, symmetry, etc. Okay, so by multiplying these two things, what we will get the power. So now these signals are what? These signals are periodic signal. So we can calculate the power for a period and then say that this power will repeat its value for every period. So we will use such power in this network each time the signal goes to this for, let's say, a time period t. So that's why we say that average power 1 over t is the instantaneous power, the p dt, the very minute power like here, and then integrating this minute power over some defined time. We replace this pt to v into I. So we replaced it and we got p is equal to integral from t naught to t naught plus t. If this t naught is considered 0, so what we will have? We will have from 0 to t, so up to 1 time period, multiply by v of t and I of t and dt, since it is instantaneous. And then we divided by the whole period, because this is average power over one period. If we do not use this, it will be a total power. So total power is not calculatable. It is always infinity for such cases. So this is our power P. Now this power will have two components as usual, the DC component and all the AC components. So AC components are multiplied by this cos of theta. Why? Because we are interested in real power. So real power will have this theta, this cos of theta, and the imaginary power would be neglected, and we are using Vnin by 2 since it is the averaged power over an interval. So if the interval is calculated by this cos, we are left with this 2. So this is pretty much easy if you consider it from this specific case, that at start we are having 0 value, and at the end we are having, let's say, p value. So what will be the average power of these 2 points? 2 points. I am saying that these things are 2 points. So all the points or all the power. So p by 2. So this is a simple explanation to this thing, that we are using instantaneous power, and instantaneous, every instant changes, the power also changes. So these are 2 instances, first instance, second instance. So 2 instance and power change. So that's why we are saying that this is p by 2. You may have your own explanation to this, but in my view it is pretty much this case. And after that, since these powers are changing, so we conclude that these all powers are dissipated as AC powers. So AC power is Vnin by 2 multiplied by the cos theta of voltage minus current. So voltage minus current will give us this angle of cos theta, the power factor. So this is the angle between V and I. So this is pretty much it. You just have to remember this thing, that we are multiplying cos theta and we are using Vi by 2. That's it. It's not that complicated. Okay. So how will we solve these numericals or questions? We are having some rules for it, and these are the problem solving rules or strategies which we will follow for finding the steady state response of the periodic forcing function. Why we call it steady state response? Because the frequencies are constant for the signals, and the signals are varying equally with respect to time. By equally means that for one time period it is same as for the second time period. So it is a steady state. Let's say the power supply to our homes is a steady power supply because it is vibrating a vibrating sinusoid, and its frequency is 50 Hz. So it is a steady voltage. The time it goes or comes, at that time it is the instantaneous. It is changing instantaneously. So it is not steady. It is the transient state. So problem solving strategies for steady state: determine the Fourier series for periodic forcing function. So first of all, what we will do is that we will determine the Fourier series for all these things. So we will determine V1, V2, V3, V0 or I, etc. for such things. After that, we will find the phasor voltages and phasor currents. So phasor voltages are calculated from these things. So if we have, let's say, some value, we calculate its magnitude by taking the real square and imaginary square and taking under root of that, and then phase is calculated by dividing the real imaginary by real and taking its tangent inverse. So tangent inverse imaginary by real is this. We will repeat this process for each and every sinusoid that we have. So you might be thinking that we are having infinite sinusoids, so we will use its first 3 or 4 sinusoids and we will calculate these things in order to find the AC power for each component. The rest of the components can be neglected because it is always decreasing function. If it is increasing function, then at infinity you will have infinite power, so that is not possible. So it is always a decreasing function. Then we will use the principle of superposition, in which the same frequencies are multiplied with one another. So use the principle of superposition to add the time domain solution for each source acting alone, and then determine the total response. So we first multiply the same frequency signals of current and voltage with one another. So we multiply, let's say, I of 60 with V of 60, not other thing, and then we add up all things. So I of 0, V of 0 plus I of 60, V of 60 will give us the power of these sources combined. If you need to calculate the average dissipated power in a network element, determine the average power in the element due to each source, and then sum up all the powers. So this is again same thing. First we are talking about the separate sources that we had, V0, V1, V2. Now we are talking about a dissipating component in it. So if you want to find the dissipating power in this, what we will do, we will first calculate the power from delivered from this, and then from this, and then from this, and then add up all things. So in that case we would have V0 by frequency base impedance, so V square by Z, plus V1 square by same, V2 square by same. Here we will also change this omega. If this is 0, we will put 0 omega in it. If this is 1, we will put 1 equal 1. If this is 2, we will put omega equal to 2. So these are the rules which we will follow before solving any example that will come next. So these rules should be learned. This is the example 15.7 from the book. In this example we are having this simple circuit. So this is our circuit. In this circuit we are having a source and some dissipating components, but we are interested in V0. So V0 is at the output of this circuit. Here we will get the components as